Anyway, we're going to cover metamorphic rock. Okay? Metamorphic rock, you still remember the rock cycle, you have two types of rock, right? So you have the igneous rock, you have the sedimentary rock, and you have the metamorphic rock. Okay? So this is the last part of that three types of rock. Yeah, so as I already mentioned during igneous rock, the origin of metamorphic rock is from igneous rock as well as sedimentary rocks. Okay? It is mainly because of heat and pressure. Now we're going to go into the third mechanism that create rocks. Okay, this is what we call metamorphisms. So in metamorphisms, it is basically tremendous heat and pressure in combination with activity of water, gas, and water and gases to promote recrystallization of rock mass. So the most important in here is that they have heat and pressure. You have heat and you have the pressure. At the same time, beneath the earth, you also have the water. Is that right? You still remember that subduction zones within that process? Okay. With that huge amount of energy, is also going to cause the friction between two materials, right? So when you have that friction between that two materials, so that is actually the one with the heat and pressure. So in here, water and gases promote the crystallizations of rock masses, including the formations of mineral into large grain, the deformations and rotation of the constituent grain, and chemical recombination and growth of new minerals. At time, the addition of new elements from circulation water as well as gases. So when you have this material, say you have igneous rock, you have sedimentary rocks. So when igneous rock and sedimentary rocks is subjected to heat and pressure, what happens is that those rock will start to melt. Okay, so moving on. The metamorphic form, contact or thermal metamorphism has a local effect. So basically, you need a contact or thermal. Thermal, as you know that it differs into the earth layer, is actually going to have much increase in temperature. So contact or thermal metamorphism has a local effect since it is caused by the heat from an intrusive body of magma decrystallizing the enveloping rock into a hard and massive body. The effect diminishes rapidly away from the intrusive. So catalytic metamorphisms involve mountain slinging process, okay, orogenic process, which are manifestation of the huge compressive force in earth crust producing tremendous shearing force. You still remember how the mountain formed and how the oceanic trench forms? Still remember? So you have those two. You have that two plates, right? Okay. Within that two continental plates, because both is actually a kind of light in density. Okay. So it is actually going up. For the oceanic trench, because both of the oceanic plates is very dense. When the very dense is very heavy, then the spell is going to go downwards. So imagine that when you have these two plates and these two plates collide, and these two plates collides, these two surface is actually going to start to have lots of frictions. So when they start to have lots of frictions, and you have the main mechanism that actually creates metamorphic rock, heat and pressure. So with that, you're actually going to create metamorphic rock swell. So this force causes a plastic flow, intense wrapping and crushing of the rock mass, and in combination with heat and water bring about chemical change and produce new materials. So regional metamorphic combines high pressure with high stresses during the rock are substantially distorted and change. Okay. So you have a two type in the metamorphic forms. This either can be in local. Okay, so this is kind of a local effect. So local effect is basically due to the contact as well as thermal of the metamorphic. Or you can look into a regional metamorphic, something much bigger, such as that mountains. So within that, when you go to the site and when you look into the say the rock, you notice that the whole region of the rock, it is actually a metamorphic rock. If it's just due to the contact, then you're going to see that only small part of a region is actually a metamorphic because it's just a contact. And the changes only happen at that particular point or that particular area. Okay, moving on. Classification. Classification for metamorphic rock is based on fabric and texture. So fabric and texture, massive fabric is homogeneous, often equigranular texture. So this is equigranular. So identify the words granular. It's actually the grain. And tree is the same. So as you can see that it is all basically the same. Okay, the second one is foliated. Okay, foliated is actually this one. You have that kind of a foliation. Repetitive layering fabric, it is band. So you can see it's band. And plateau structure providing witness plane that result from high directional stresses and include three forms. So you have banded or lenticular. Most of the time people will call it banded. Schistosity and Slaty cleavage. So foliation is actually this one. You can see that repetitive layering, okay, of a rock. Okay. You would see this most of the time with the wood grain. But if you see this in rocks, this is actually only happen to the metamorphic rock. So moving on, so the classifications, you have the texture and you have the fabric. So in the texture, you have coarse, medium, fine to microscopic, and others. Okay, others is basically based on different materials that is already mixed up. In fabric, when you see a foliated metamorphic rock, this is an example. If you go right, then with massive metaconglomerates, then in medium you can see schist, mica, chloride, and in massive you can see quartz, marble, serpentine, soapstones. In this type of rock, highlight slates, you're going to see that the fabric most of the time is foliated. And in this massive, most of the time the fabric is actually they have kind of a equigranular. To see rocks, all you can see is actually the features of that rock. Okay, this is other forms. You have magmite, complex composite rocks, intermixture of metamorphic as well as igneous rock. Mylonites formed by intense mechanical metamorphisms show strong laminations but original mineral constituent and fabric crush and pulverize formed by differential shearing movement between beds. Foliated, and this one is fine texture. Okay, so this one you can see in fine texture. So this is example slates. Okay, this is Slaty cleavage. Okay, this is slate stones. In Slaty cleavage, parallel foliations layering of fine-grained slaty minerals in the direction perpendicular to the direction of maximum stress, defined as having less than 0.01 mm, very small space occurring between the layers. Into the second one, schistosity. This is the second type of foliations. Second type of foliations, micaceous, is this example of the rock. Schistosity, layering in the coarse grain, and crystalline rocks due to the parallel arrangement of slaty minerals grains such as muscovite and biotite, usually run planar through the rocks, and that is, it all runs the same directions. In the large specimens, however, the foliation may be folded. Schistosity differ from slaty cleavage in both grain size as well as mineral content. In comparison to the slaty cleavage, this schistosity is basically they have much bigger grain size, as well as the mineral content is actually the one that within that grain size that you can actually see its layering much more visible compared to the slaty cleavage. So this is schistosity. So next one is banded. This is the most intense form of foliations. So you can see here. This is what we call banded. This is layering of that rocks. And layering of that rocks, since this rock is formed from minerals, right? And within these minerals, it is subjected to heat and pressure. So the most intense form of foliation, the layering in a rock in which bands of granular mineral, quartz and feldspar alternate with band in which eliminates minerals predominates. At the highest grade of metamorphisms, mineral begins to segregate into separate bands. The micaceous minerals separate from the quartz as well as feldspars. This is considered as the highest grade of metamorphic rock, like this one in mixed texture, okay, magmite, a rock in which metamorphic texture, schistosity or mineral blending intermixed with igneous texture, coarse grained igneous rocks. Only the rocks has not yet completely melt and is fractionally melt. So this is to show that with different materials, they have their own different melting point. So with the different melting point, you're going to see that some of the minerals is actually mixed. Some of the minerals, they are just going to maintain as is. So moving on to metamorphic grades. So in metamorphic grades, you have from a low grade to a high grade. So low grade is basically that slates, okay? That's like cleavage. And genesis in this one is banded, okay? So this is cleavage and schistosity bending. So it's actually the high grade. So in here you can see that the crystal size is also increased. So the left is low grade, the right is actually the high grade. Okay, this is metamorphic derivative. Okay. You have type from sedimentary rocks and you have from igneous rock. So this is the parent rock. Okay. So in conglomerate, in sandstone, shales, limestones, when it's metamorphic, then it's going to change to, say, limestones is going to change to marble. Shale is going to change to slate, spiral, and bridges. From igneous rock itself, you can actually change from igneous rock to metamorphic rock, and at the same time, from the metamorphic rock, when the material is melted, then it's going to change, become magma, and this magma can actually change to a igneous rock again. So that's why during the igneous rock class, as initially I'm showing to you guys this one, I call it the rock cycles. People call it a rock cycles because within all these materials, it can actually changeable between one and another. Okay. Okay. So any questions regarding metamorphic rock or anything, rock cycles or anything that's related to my part? Okay, thank you.